last but not least, let's talk friction. It is another resistive force, and what it resists is relative motion. So this is a resistance to relative motion, or an attempt at relative motion, I should say. You can kind of think of it as if you're walking, to go anywhere, we need to push something backward. So you are pushing the ground backward. Well, according to Newton's third law, every action has an equal and opposite reaction. So the action of you pushing on the ground will cause the ground to push you forward. And you can think of that as, like, if this is your shoe, you are sliding your shoe this way on the ground, and the friction wants to resist that motion, so the friction is going to push forward. And it's always directed parallel to the surface. And if we keep that in mind, so if this is the force of friction, the ground is also going to try and keep you from going through it. So you're pushing down on the ground. The ground is going to push up on you. Both of these forces are being provided by the ground, and they're perpendicular to each other. What that tells us is these are components of the same force. We could say that the ground is not only pushing you forward, it's pushing you upwards. So this is the force from the ground. So keep that in mind. Normal force and the frictional force should always be perpendicular to each other. With that being said, friction typically depends on two things. It is proportional to the relative roughness of the surfaces. We represent that with the coefficient of friction, and that's the Greek letter mu, or mu, I don't know. Either way, so the coefficient of friction times our normal force. So hopefully that makes sense. The amount of friction on a surface depends on how rough or adhesive the surface is and how hard we're pressing against that surface. One quick exercise you can do is you can take your hands and smack them together, rub them past each other really quickly, and then smack them against each other again and push really hard and try to move past. It's kind of hard to do that while pushing against the other hand. For one thing, our brain is trying to focus on two things at once. But you can even do this with like a heavy object on a carpet or a rug versus a light object. Try to slide both of them across the rug and you'll notice a difference. So there are no other tricks or constants or anything here, but there is something to be mindful of. There are two types of friction. There is static friction, and there is kinetic friction. Static friction is resistive, and it's only going to apply as much as it needs to. So if we go back to trying to push that box on the carpet, that heavy object on the carpet, if it's just at rest, if it's stationary, we're talking static friction, static stationary. And if you push on the box with 20 newtons, and the floor can provide a resistance of 25, that would be a little bit weird for you to push on the box and it suddenly accelerate towards you. The floor is not going to provide 25 newtons, it's only going to provide the 20 that it needs to. So we can say that the static friction can be less than or equal to the coefficient of static friction times the normal force. So friction is fun. F-U-N. If you can remember that, you're good. The kinetic friction, once you get the box going, it just depends on the normal force and the coefficient of kinetic friction. And typically, your static is going to be a greater magnitude than your kinetic coefficient. So your static coefficient typically always higher. I can't think of any examples where it isn't, but I'm hesitant to say it's always higher. And so that relative roughness or adhesiveness is just, or cohesiveness if the two surfaces are the same, is just the ratio between the frictional force and the normal force. So I want to go back to the whole opposing relative motion thing. Notice here is our example of walking. It's propelling us forward. So it's actually in the direction of our motion, but that's because our feet relative to the ground are trying to move, or we're trying to move them backward to generate that motion. Another way you can think about it is, let's say we have a flatbed truck and we have a box here. If the surface is rough enough, that box will just stay in place. So as this car is moving forward, the box would also be moving forward. Well, what's keeping it in place is that friction. So let's think about this real quick. If it wasn't rough enough, the car would just slide out from underneath the, or the truck would just slide out from underneath the box because of Newton's first law. An object at rest wants to stay at rest, that law of inertia. So this box really just wants to stay put. But relative to the truck, if it just wants to stay put, that box is moving to the left, or not the left, but it's moving behind the truck. So if you were watching this happen, it would look like it was moving away from you. So if we go back to where the surface of the bed is rough enough, or the box is rough enough, it doesn't, either one, as long as they're sufficiently keeping the box in place. The box relative to the truck wanted to move to the left. That means our frictional force is to the right. That's what's propelling the box forward along with the truck. And when the surface can't provide that, that's when the box moves and we switch to a kinetic friction. So it would start sliding away from the cabin of the truck. So static friction, stationary, kinetic when it's in motion. And that's all I got for you on friction.